I want to show you how there's more to the universe than meets the eye. In fact, how there's more to the universe than is even currently understood by science. My talk is about the dark side of the universe, a side that's unseen, unknown, and how we're trying to solve it and investigate it. Now, before I start talking about what we don't see in the universe, let's just start off with what we can see in the universe. So take a moment to just look around you. Look at the vast diversity of things you can see, all the different people, this stage. Think of what you can see outside. You can see buildings, you can see oceans, you can see countryside. You can see the stars and the planets and the moon at night. Now, everything out there, everything in here, it turns out, even though it looks very, very different on the surface, when you get down to it and you look at it at the smallest distances, everything is made of the same basic constituents, the same few types of fundamental particle that are the building blocks, the ultimate building blocks of all stuff, all matter. Everything is held together by the same few fundamental forces. Everything obeys the same few laws of nature. And that applies to everything that we've seen and measured and studied around us on Earth. It applies to everything even further afield, out in the solar system, where we have planets, comets, meteorites instead. And it even works if you go further and you look into the galaxy and you study the stars around us. It even works if you go further still and you look as deeply into the universe as it's possible to see with telescopes. Everything we've studied fits this very simple picture that we have in physics of what things are made of at their deepest, most fundamental level. And it really works well. And that is wonderful. But as you might have guessed from the fact I am standing here giving you a talk, that isn't all there is to the story. There is a catch. And the catch is that there's more to the universe than meets the eye on first inspection. And I want to show you what that is in my talk. So the first clue that there's something else out there that we haven't understood yet comes from looking at galaxies, like the one you can see behind me, and measuring how fast a galaxy spins around. Now, you can work out how many stars there are in a galaxy just by how bright it is. And if you know how many stars there are in a galaxy, then you know what the gravitational force is keeping that whole galaxy together. And if you know how strong that gravity is, you know how fast that galaxy can rotate before it starts to break up, before the stars fly off and it stops existing. Now, the catch is, when you make a measurement of how fast these galaxies are going round, you find out that they're going way too fast, far too fast. These galaxies should have broken up ages ago. They shouldn't even be here. The fact that they are here, the fact that they're stable and they exist and we can measure them, makes scientists think that there's got to be something else there, some other stuff inside galaxies, stuff that we can't see, but which is massive. So it supplies the extra gravitational glue that is keeping the whole thing stable. Now, this invisible stuff that we can't see, we call it dark matter. It's not dark because it's in shadow. This dark matter doesn't absorb or reflect light at all. We call it dark because it is a complete and utter mystery. It really is. We've got no idea what on earth this stuff is. So now you're probably thinking, oh, hang on a minute. This is a bit stupid. Why are you inventing an entirely new thing in the universe just because you can't understand something? Why do you need such spooky stuff? And it's true. Perhaps we don't really understand how gravity operates. Perhaps you've misinterpreted something. But there are other clues out there that make us think that this strange invisible stuff really does exist. Let me give you another one. This is a picture of something called the bullet cluster. The bullet cluster, two colliding clusters of galaxies 3.7 billion light years away. Now, astronomers can measure how much stuff there is in these colliding clusters. They can measure the stars and the gas by looking at it through telescopes. And that's what you see behind me. You can see the stars directly, and the gas has been colored in red, so you can see it. Now, independently from that, scientists can also measure the distribution of stuff in those colliding galaxies as well. And they can do this by looking to see how tightly light is bent by gravity as it moves through this area. The more massive stuff you have there, the more tightly light is bent. And in this way, they can build up a map of where stuff is in that galaxy, and that's shown in blue. Now, if you just look at that blue area and you compare it to the stars and the red gas, you'll see it doesn't really overlap it very much. And yet, if you look at that blue area through a telescope, you don't see anything. Now, you can't explain this sort of behavior by changing the way you understand gravity. This sort of behavior can only be understood if you realize that, well, that stuff that's there that you can't see, yet which is changing the way gravity seems to behave, it's dark matter again. This mysterious stuff we can't see is responsible for this behavior too. And bit by bit, all these clues start to pile up to give you evidence that there is something new out there. So dark matter, it seems, is an intrinsic part of our universe. It's such an intrinsic part of our universe that scientists who write programs to simulate how the universe ages and evolves find that they have to put this mysterious dark matter in. Otherwise, they can't even get galaxies to form. And the universe they end up with is an entirely different place to the universe that we live in. And that means that dark matter isn't just intrinsic to us, it's important, incredibly important. Dark matter is one of the reasons why we're here. Without dark matter, we wouldn't be on a planet orbiting the sun, orbiting around a galaxy. We just wouldn't exist. That's how important dark matter, this mysterious stuff, is to us. And it's not like this stuff is rare either. In fact, if you counted up, 85% of all the stuff in the universe is made of the dark matter type stuff. And it turns out that only 15% of all the stuff in the universe is made of the visible matter that you can see. The visible matter that we started with at the beginning of my talk. Stars, planets, atoms, people. A mere 15% of the universe. Now think about that for a moment. That is shocking. That means that we don't understand anything. It means that 85% of the universe is a complete mystery. And it's a really important 85% of the universe as well. And if you're a scientist, you look at this and you think, I'm desperate to understand that. How on earth can I understand what that stuff is? I want to know what dark matter is. I want to know what it's made of and how it behaves. That's what drives people like me to do science, to find out questions like this. Now, we don't know what this stuff is, but we do have lots of ideas about what it might be. Let me give you a few examples. Dark matter might be made of very, very light particles called axions, or more massive, weakly interacting particles called WIMPs. Or it might even be a more exotic version of something we already know about, like a neutrino. Dark matter could be hidden in a dark sector of the universe that you can't see, or hidden dimensions of a universe that you can't see either. It has even been suggested by some people that dark matter is responsible for wiping out the dinosaurs. Wow, that's an all-encompassing theory. Now, there are so many ideas here. They can't all be right. And maybe none of them are right. How on earth do we find out which of these, if any of them, are right? Bearing in mind that you can't see this stuff, you can't detect this stuff. How do you do it? it's really a challenge. It's really difficult. And the best way we have of making inroads into this is to use science and to build experiments that take data that we can then use to test the predictions of all those different theories that tell us what dark matter might be made of. And if we find one that matches reality, then at that point we might have identified what dark matter is, and then we'll be able to understand it. That's our plan. And some of these theories can be tested where I work, at the Large Hadron Collider facility at CERN, the European Centre for Particle Physics. Now, you've probably heard of the Large Hadron Collider. It's this enormous machine, 27 kilometers long, 100 meters under the ground, and it's our telescope into the subatomic universe. Because the Large Hadron Collider reveals to us what matter is made of at the very smallest scales. It allows us to sift through matter and work out what fundamental particles there are that make it up. When this machine operates, we have two beams of protons circulating around the ring in opposite directions, accelerated until they're traveling a few meters per second less than the speed of light. And then we bring the beams into collision at 4 points around the ring where we build our experiments. And this doesn't happen once or twice. This goes on 40 million times a second. What goes on when those proton beams collide, which is key to our whole investigation? Because when proton beams collide, for a tiny instant of time in a tiny area of space, what we're doing is creating the very high temperatures you need to create fundamental particles. And these zip out from the collision point at high speed, depositing energy, decaying to more stable particles as they go. And our experiments act as gigantic three-dimensional digital cameras and take a snapshot of the particles that have been produced and are left behind. And it's by studying these snapshots like this, that we can work out what fundamental particles are hidden at their heart, what fundamental particles were originally produced in the first place to give rise to what we see. Now, we have to be clever if we're going to do this. It's not easy, but we can do it. And because we can do it, that allows us to work out not only what fundamental particles make up the matter we see and understand, like atoms, but also potentially to identify the fundamental particles that make up the stuff we don't yet understand, like dark matter. That's our hope. Now, the way we do this, if I'm honest, isn't really rocket science. The idea is really quite simple, because what happens is when a fundamental particle is produced and then decays to other particles, those other more stable particles get absorbed in different regions of our experiment. And that means we can identify which particles we have by where they're stopped. And once we've identified which particles have been produced in a beam collision, then we just compare that collection, that experimental signature, to that we expect to be produced by different fundamental particles being produced in the first place. And when we find a match, then we make an identification. That's how we work out which fundamental particle we had at that point. We're really, if you like, subatomic collision scene investigators, because what we do when we analyze data is we turn back time to work out what happened at that point when the beams collided. Now, the key to this is not just looking at one snapshot. We have to look at millions, trillions of these, because it's the only way to work up a picture for the different types of fundamental particles that there are out there in the universe, even the rarest ones. And we think the ones that make up dark matter have to be pretty rare, otherwise we might have understood it already. So the way we think about this is that if we have a collision and part of the signature we see matches something unseeable, undetectable like dark matter, but the rest of the signature matches the way in which you expect dark matter to behave inside your experiment, then that is the way that we're going to work out what's happened. We'll take that signature and we'll match that to predictions that our dark matter theories give us. And if we find a match, if we can make an identification of that, then that would truly be momentous, because that would mean not only have we worked out which one of these theories is true, but we would have worked out what 85% of the universe it's actually made of. It would be an amazing discovery. And it's the sort of discovery that we all live for, that we really hope to make every time we analyze this data. And that's why we do it. We want to find out more all the time. Now, one of the most popular theories that we've tested at the Large Hadron Collider that might explain dark matter is a theory called supersymmetry. Supersymmetry extends our understanding of the universe and suggests that there might be a connection between force and matter. And the way it does this is to predict the existence of many new fundamental particles in nature. One of these new particles is experimentally unseeable, undetectable. That's the one that we think makes up dark matter. But the other particles we should be able to see in our experiments. And so we think if we can make discoveries of these new particles and identify those, then we'll be able to infer that this other unseeable particle exists. And that will mean that we'll know that dark matter is really a supersymmetric type of stuff. We'll have worked out what it is. This picture is from one of the Large Hadron Collider experiments, but the other experiments tell a similar story. And what this is a tabulation of each type of supersymmetric particle we've looked for in different versions of the theory, behaving in different ways and manifesting themselves using different experimental signatures. And the colored lines you see behind me show where we haven't found any evidence for those particles. They show the masses that those particles cannot have, otherwise we would have already discovered them. And as time goes on, we analyze more data and see the same thing. Now, some theorists think that supersymmetry is such a good theory that they don't want to give it up, despite what we haven't seen. And it's true that we haven't ruled out supersymmetry. We just haven't found any evidence that it's true. It's quite possible that these particles might be a little heavier than we expect. They might be just out of reach. And to find them, we have to look in more data, maybe in different experiments, before we can settle the question. But more importantly, we have to try other theories that might explain dark matter and test those to see if they do a better job than supersymmetry. That's the problem with this theory. It really is the theory that keeps on giving. It's very hard to disprove. But whatever happens, there are so many investigations on, and we're so determined to find something. You can be sure that we will learn more about the universe, both in what we can see and what we can't. Thank you very much.